Okay, good afternoon on my behalf. My name is Jaakko Leppäniemi, and I work as a senior scientist and a project manager at VTT. And I'm thankful for Kasha and the others at TechBlick for asking us to present this our recent work on high resolution printing. And like the title says, our aim is to take the accuracy of printed electronics beyond 1 micrometer level. We have been working on a high resolution printing method called reverse offset printing, or ROP in short. So at the center you see our new 8-inch compatible sheet-fed reverse offset printing system. And this ROP method is based on three main steps: coating, off, and set steps. So first, ink is coated on the top of a PDMS roller, where the ink is let to reach semi-dry state by partial absorption of the ink to the PDMS and evaporation. And the ink has high cohesion and viscosity in this semi-dry state. Next, in the off step, the semi-dry ink is patterned on the top of the PDMS using a high-resolution printing plate, which removes unwanted portions of the ink from the PDMS. And this plate can be fabricated using standard micromachining techniques down to sub-micron resolution. Then, in the final set step on the right, the patterned ink is transferred from the PDMS to the receiving substrate. And as a result, micron level resolution with uniform film thickness and good edge definition can be obtained with pattern widths that are close to the nominal sizes. So these are features that cannot be typically reached with other conventional printing methods. Next, I will introduce two critical aspects that enable a wide range of applications in flexible electronics for high-resolution reverse offset printing. So first, the overlay accuracy between two layers is critical for multi-layer structures and devices such as thin film transistors. Our ROP system has an automated camera-based registration system for both printing plate and the substrate stages. And here we have data for overlay accuracy between two printed layers in one sample. In this test, after printing of the first layer, the sample was removed and the nanoparticle ink was cured, and the sample was then installed back for the second layer of printing to emulate the real process conditions. And you can see that the overlay accuracy is at 2 micron level with a smaller variation in the cross direction than in the machine direction. As a second aspect, the ROP can be also used as a resist printing method to enable a very wide materials palette. So conventionally, nanoparticle inks, polymers, and metal oxide precursors have been printed with ROP. However, this material selection is still limited for ROP and in general in printed electronics. For example, low work function metals like aluminum or metal oxides like ITO are hard to print as inks. So this material palette can be expanded by VTT's ROP-based lift-off patterning process. So in short, we basically print a high-resolution polymer pattern on a substrate with sharp sidewalls, and this allows the patterning of evaporated or sputtered films at micron level resolution. The materials include metals like aluminum, gold, copper, and oxides like ITO. And down here in this right-hand corner, you can see sputtered ITO patterned at few micron resolution. So the applications for ROP, they range from transparent metal mesh conductors to displays, memories, biosensors, and millimeter wave applications. So here are some examples of micrometer level printing using our reverse offset printing system. So on the left side, we have a 1 micron dot array printed for filter application. We can also fabricate isolated wirings and electrodes down to 0.5 micron resolution. And then here you can see a PET foil with transparent metal mesh conductor with 1 micron line width and good transmission in the visual range. And also oxide and organic TFTs with feature sizes below 10 microns are enabled by this high overlay accuracy at micron level. So with this, I would like to thank you for the attention and also our funding agencies that have been supporting this work.